So welcome back. Taking the discussion that we had about the progressive traveling mechanical waves a little further, let's recall that for the transverse waves we had these two equations: y, the disturbance x comma t, is equal to cos of omega t minus kx minus omega t plus phi in the positive x direction, it's moving in the x plus direction, and this is when it is moving in the opposite direction, that is x minus direction. The equation goes like this. There will be occasion when I will let you know how these equations are derived at the end of the lecture. Okay. K is equal to 2 pi upon lambda, where lambda is the wave number. Okay. K is 2 pi upon lambda. Lambda is in meter and K is in radian per meter, which can be dropped. Radian can be dropped and it can be written as per meter. Omega is equal to 2 pi upon capital T, where T is in second and omega is in radians per second. Okay. Now this is about the transverse waves, and for the longitudinal wave I have the longitudinal disturbance Sxt, which is along the direction of propagation, okay, for longitudinal waves. And of course, instead of taking cos, I have taken sine. Doesn't matter at all, okay, because they are replaceable with each other. Only the discussions you have to be careful, okay. Now A, here are, oh sorry, this is A, cos, okay. So A and A, they are the wave amplitude. That's the maximum disturbance that is there. Phi is the initial phase. Initial means that when x is equal to 0 and t is equal to 0, then this becomes A cos of phi. Okay, so because initial means that only t is equal to 0, but here I will say that it is the phase, this thing. One thing I want to make clear to you here also, that this quantity kx minus omega t plus phi, this is the total angle and this is the total phase, like that. Okay. Omega is also equal to 2 pi nu, nu is equal to 1 upon t, so frequency is in hertz, also known as, old unit is cycles per second. Okay. Now let us take, try to find out the speed of a traveling wave. In this case we are taking the transverse wave, okay, and this is the two snapshots. One is the black color and another is the red color. After this is black color is the time t, and this is at the time t plus delta t. Then we find that the two snapshots that we take, when they are put together, there is a constant. You take here or here or here or here, anywhere, there is a change in the value of x, because this is a y versus x diagram. Okay, that's what I call a snapshot. So on a string, this is actual diagram that we'll get. So what we conclude is that the disturbance moves a distance delta x in time delta t. Clear? So motion of a fixed phase point, what is there? The kx minus omega t is equal to a constant. So I can write it that k x minus omega t will be equal to kx plus delta x minus omega t plus delta t. Two different values of x and t. Okay. So when you work it out, so kx and ks minus omega t and minus omega t, they cancel out each other, and what we are left is k delta x minus omega delta t is equal to 0, which gives us delta x upon delta t is equal to omega upon k. In the limiting case that delta x is equal to 0 is nearly equal to 0, in the limit tending to 0, delta x also tending to 0. So I can write this delta x upon delta t in the form of a differential ddt of x, which is defined as the wave velocity. This becomes equal to omega upon k. Omega I can write as 2 pi over capital T and 2 pi upon lambda for k, and this turns out to be equal to lambda upon t. Okay. So wave velocity is the wavelength lambda divided by the time period. Okay. So this is a relation which is general relationship. We will also establish with the help of these two equations that d2y upon dt2 divided by d2y upon dx2, in either relation, this turns out to be equal to the square of the velocity. And this is the general test that any wave, traveling wave, should give us. Okay? So we talk more about it. So now let us, after defining the velocity that we had, okay, as equal to the lambda upon capital T, which is a general definition, we now try to find the speed of a transverse wave on a stretched string. Okay. So the material medium there is a string, and the string has got associated tension in it. When it is stretched, then the material has two properties associated with it. One is the restoring force which is set up in the medium, which is, I am saying, number one, and the other is inertial properties, that is the mass density associated. These are two properties which we can see apparently. Now, what we find that speed is expected to be directly related to the restoring force set up in the medium. That is, if the tension is more, then the speed may be more. And if inertial properties, the mass density of the medium, if the mass density of the medium is more, then the speed is expected to be less. These are some expectations, broad speculations. Okay. Now I can say that the restoring force is inhibit in the tension. Sorry that I have to use T for different things, okay, because of the paucity of terms, but I will have the tension described here. This is not the time period. Okay. Then the inertial part I define in terms of the linear mass density, the mass per unit length of the string. So where m is the mass and L is the total length of the string in which the progressive wave is traveling, so m upon L is equal to mu. Now this can be shown by rigorous calculations that the velocity will turn out to be equal to under root T upon mu. Okay, but that is not essential that we go into the details, and find out this relation. So what we do? One of the methods we know that if we can say as to what are the things on which certain thing is depending on, then we can do a dimensional analysis. So if suppose this is the kind of relations with dimensions on the left hand side and dimensions on the right hand side should be the same. Now tension, which has got the dimensions of force mLT minus 2, mu, which is the mass per unit length, is ml minus 1, and the velocity is lt minus 1. Now one thing which is not very funny, but we can say by inspection, mlt minus 2 divided by ml minus 1, this will turn out to be equal to L minus L2 L square T minus 2, which I can write as Lt minus 1 whole square. So this is the dimension of velocity. So we can write that the velocity square is equal to tension upon the mass per unit length, which leads us to this equation. Okay, but by inspection I don't subscribe to you. Instead I will say that please resort to what is dimensional analysis, and in doing so I write mLT minus 1. Now let's say that this first term, which is the tension, and the second term, which is the mass per unit length or the linear mass density, they have got the indices alpha and beta respectively. We multiply them together and then equate the indices are the powers of m, l and t on this side and m, l and t on this side, and then we work out those equations, and therefrom we can find the value of alpha and we can find the value of beta, and the value of alpha and beta are such that we can write finally that the velocity of the travel of a transverse wave in each direction is equal to the same v is equal to T upon mu. So one of the spillouts I forgot, but this is also true for anywhere, that the velocity was given universally to be equal to the wavelength divided by capital T, which gives another relation v is equal to nu lambda, because 1 upon t is equal to nu, r lambda is equal to v upon lambda, also lambda is equal to vt. So all these relations are identical relations, just like trigonometrical identities. So any of these equations you should be able to derive it, any of this equation from the basic equation v is equal to lambda upon t, or v is equal to nu lambda in a moment's time, not more than 2 seconds. Now let us take the travelling wave velocity, okay, in a homogeneous medium for longitudinal waves. Okay, so you have to see about what kind of a elastic property is there and what kind of inertial property is there. The elastic properties in the case of bulk of the matter is the bulk modulus of elasticity B, which is defined as delta P over change in the value of the pressure divided by this delta V upon V, which is the strain. And naturally, because this has got no dimension, so it has got the dimensions of pressure, which is ml minus 1t minus 2. Okay, how I remember it? mlt minus 2 divided by L square, okay, per unit area, and the unit is Pascal or Newton per meter square. The inertia part is represented by the mass density. Rho is equal to the mass divided by the velocity, okay, which is the mass density of the material, which is dimensionally ml minus 3, okay, kilogram per meter cube. Well, By the way, at STP, the density of air is 1.29 kilogram per meter cube. Okay, that should be borne in mind. Now, ml minus 1, t minus 2, ml minus 3, and like some people say, and they have argued this, that by simple inspection, of course, ml minus 1, t minus 2 divided by ml minus 3, this turns out to be equal to L is mm cancels, here comes L square t minus 2, which is L t minus 1 whole square. This is for velocity, and this is for B, and this is for rho. Okay. So when the dimensional analysis is made, how will you do the dimensional analysis? It's very simple. I will say that the dimension of the velocity is equal to this raised to the power of alpha into this raised to the power of beta, okay, and then equate the indices, the powers of m, l and t, and finally you obtain that this is equal to c into under root b over p, where c is an undetermined constant in the dimensional analysis. This similarly you could have it in the other case also. Of course, this is a dimensionless constant, undetermined dimensionless constant in the dimensional analysis. And we find, when we do that, we find that the value of c is equal to 1. Okay, so no matter, then the velocity turns out to be equal to under root b over rho. B is the bulk modulus and rho is the mass density. Okay. Which, as I will show just now, in the case of a gas, turns out, B turns out to be equal to P divided by rho, okay, where B is equal to P in the case of gases, as I am going to show you just now. In the case of solid rods, where there is a longitudinal wave propagation, the velocity of the longitudinal waves in the case of the solid rod turns out to be equal to our friend Young's modulus y, which also has got the same dimension ml minus 1 t minus 2, and rho of course which has the dimension ml minus 3. So solid rod, we get the velocity is equal to under root of Young's modulus of elasticity divided by the mass density of the system. Now, as I said, I will show you that from the equation PV is equal to an RT or KB in a T, okay, that the bulk modulus of velocity can be defined as the pressure in the case of gases. And this kind of an equation, this is the Newton's equation. When this equation was studied and the velocity of sound in air was calculated and also determined experimentally, there was a lacuna between the two of them. There was a mismatch, and this mismatch also I am going to address next as what is known as the Laplace correction and give reasons for that. Okay, then we had the velocity as equal to under root b upon rho, okay, and for that, if I recall the ideal gas equation, where n is the total number of molecules in a confine of volume V at a temperature T, the pressure is P, and Kb is the Boltzmann constant. I am not going to give the details. Okay. The changes that take place during the propagation of traveling waves in the longitudinal waves, it was considered initially that whatever is happening isothermally. And remember, isothermal processes have to be very, 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 very slow. Okay. Anyway, so PV is equal to Kv is a constant, M is a constant, T is a constant for the given volume, so PV is equal to a constant. Okay. If we differentiate this, this will turn out to be equal to V delta P plus P delta V, or P delta V plus V delta V. This is equal to 0. The other side is constant, it's not variable. So this gives us the value of P as equal to minus delta P upon delta V over V, which is nothing but the definition of the bulk modulus of elasticity. Okay. So as it is, and as I told you in the last frame, that V is equal to P upon rho, under root. Well, this was proposed by no one other than Sir Isaac Newton, the great man, okay, who couldn't get the idea because he was a multifaceted person who was working in multiple directions with a lot of concentration, being divided here and there. So anyway, when I calculate this value of V at the STP, standard temperature and pressure, is also called sometimes novel temperature and pressure, we see that the value is about 280 meter per second. But the experimental value at that STP is 331 meter per second approximately. Now, this was a big lacuna. Then came Laplace. He made a correction. And the correction is that instead of the isothermal process, he said that the process is adiabatic. Compressions and rarefactions which take place in the longitudinal waves, okay, they are more sudden than not. And therefore, the process over there should be adiabatic. Means no energy will go out of that particular zone where the changes are taking place, and no energy can come into the system. This is called adiabatic system. The adiabatic system we have, instead of PV is equal to constant, we have PV raised to the power gamma is equal to constant, where gamma is the ratio of the two molar specific heats, the one at constant pressure divided by the one at constant volume. Okay. So, if we differentiate that, I'll get delta P V raised to the power gamma is equal to 0. Now these are two product of two functions. So what is the value? The first function into the differential of the second function plus the differential of the first function into the second function. So if I apply that rule which I have uttered, said in words, so this becomes equal to first function P, the second function V raised to the power gamma minus 1 into delta P, okay, plus delta P, the differential of the first function into V raised to the power of gamma, that is the second function. This is equal to 0. So when I work it out, it happens that minus delta P upon delta V over V, the stress upon strain kind of a thing that is occurring over there, is by definition the bulk modulus of the system, which turns out to be equal to gamma P. Okay. So instead of B being equal to P as we have taken over here, the Laplace correction is that man take gamma over here, and gamma P upon rho, this turned out to be like this. And gamma for air is mostly nitrogen molecules and oxygen molecules in the ratio of 4:1 plus some little bit of this gas, that gas, this, which is negligibly small. So we can say that for air, the system is almost diatomic. And when we make the calculations, putting the value of gamma as 7 by 5. 7 by 5. Okay. Cp minus Cv is equal to what? And remember, the degrees of freedom for the diatomic molecules is equal to 5. What are they? 3 degrees of translation in the mutually perpendicular directions x, y and z. And because the two molecules, for a molecule like nitrogen or oxygen, the atoms are situated over here, then they can have a rotation like this or like this. So there, of course, there will not be a rotation in this direction. So 3 degrees of translational motion, freedom, and 2 degrees of rotational freedom, that makes 5. And then there comes 5 by 2 R and 7 by 2 R for Cv and Cp respectively. So this turns out to be 7 by 5. The velocity, if we calculate like this, then it turns out to be equal to 331.3 at the same STP. I'm told, and that initially this correction of this gamma didn't come when you think of this process to be adiabatic. That was the later explanation. But it just substituted a correction over here and just to bring out this value, and that turned out to be equal to correction value over here was 1.4, which I insist that we write it as 7 by 5 for nitrogen, for oxygen, for hydrogen, okay, any diatomic molecular systems, or the ensemble of diameter. Of course, here carbon dioxide will be there, ammonia will be there, one neon, argon, xenon, this, that, and even H2O will be there. Okay, so friends, we have come to the conclusion that for the material waves, the waves which are progressive, which are traveling, which are mechanical, and they are longitudinal, we have an equation like this. This is the velocity of sound, and that correction with that, and the explanation is for adiabatic thing, okay, because this happened in the 17th century when during the lifetime of Newton. So this was much appreciated and this was explained. By the way, I have gamma p upon rho and I have this. Okay. Now, if we add water vapor to it, a plenty, maybe 5%, 10% like that, what will happen to the velocity of sound? Imagine, the pressure will be almost the same, but the atmospheric pressure will not change much. But the value of rho, which is the density, volume density of the air, that becomes less or that becomes more? The answer is, and I will share with you what some student told me. Okay, what a beautiful explanation she gave. But what I am going to tell you, that when in air enters an H2O, so the number of molecules in a given ensemble has to remain the same. So it replaces one of the molecules of nitrogen or oxygen. Nitrogen 28, oxygen 32, H2O, water is 18. Okay, so 18 replaces 28 or 32, and therefore the total value of this becomes less. And when this is less and this is fixed almost, then the velocity becomes less. So with how the velocity of sound changes with the changes in temperature, etc., etc., that's another point which we may discuss towards the end. But just now I'll share with you the argument of the student, the lady, and she happened to be my brother's daughter. She was a very intelligent girl. And when I asked her, why is water vapor lighter than air? Then she gave it a thought. Yes, it should be lighter than air. I said, why? She said, if it were heavier, then the floors will get wet because they will settle down because of gravity. Well, that was an explanation that was given by a very young mind, but nevertheless a thinking mind. I hope that all of you have thinking minds, and let us say this lecture is lecture number 100 during the corona time. So a big hand to all of you for being with me and encouraging me to deliver these lectures for you. Thank you very much. Thank you very much. Thank you very much.